In exercise 2174, we're trying to make Tylenol, acetaminophen, from the vapors of gasoline, benzene. So the question says, starting with benzene and using any other reagents of your choice, devise a synthesis for acetaminophen. Now, when you look at acetaminophen from the perspective of this chapter, you would see a carboxylic acid derivative. You have a carbon double bonded to oxygen, single bonded to an amine. So that's an amide. And we can make that from two carboxylic acid derivatives. Now, on the one hand, we would know that this group on the left would have had to have come in as a nucleophile. So that's one thing that we're going to need. We're going to need that nucleophile, benzene with an alcohol and an amine that are para to each other. And notice there are two hydrogens here to stabilize that nitrogen. Otherwise, it would have a full negative charge, would be really reactive. We can always do a proton transfer to take it off after it attacks in the nucleophilic acyl substitution. Now, we often use, and if we draw those retrosynthetic arrows, meaning how do you make this from this previous product, those have sort of two parallel lines and a really fat arrow. So we could make this from, normally we would use something like this and we'd use the most reactive derivative of carboxylic acids, the acid chloride. However, this may have a side reaction if we have, as we'll see, we may have some catalyst left over in our beaker. And this could have a side reaction of Friedel-Crafts, where this would add onto the benzene ring itself rather than onto the nitrogen. Now, that's a chance, but you could protect against the chance just by not using this chlorine here. In other words, by replacing it by another really reactive carboxylic acid derivative, and that's the anhydride. So that, using the anhydride rather than the acid chloride, just helps to prevent any side Friedel-Crafts reactions that may occur by a fluke. So that's what we're going to use here. Notice that in that comparison, if you compare those two molecules, this whole big fat group is just the leaving group, just like the chlorine. So it's really an analogous molecule. Okay, so we know we can make Tylenol from these two pieces. If we were to react these two pieces together, we could make Tylenol. But they wanted us to start from benzene. So how can we turn benzene into this? How can we make this transformation happen? Well, we want to put two things onto this benzene ring. We want to put a nitrogen, an NH2, and we want to put an OH. And those are going to require very different types of reactions. First, the nitrogen. We only learned one way to put a nitrogen onto a benzene ring, and it was nitration. That used nitric acid, HNO3, and sulfuric acid, H2SO4, to put an NO2 onto the ring. So if we're just drafting, if we're just like making a rough draft, sort of brainstorming, if we had a benzene ring and we do nitration, HNO3, H2SO4, that will put an NO2 onto the ring. And remember that an NO2 is a meta-director and a strong deactivator. So meta-director and strong deactivator. We see that these are para. So we definitely wouldn't want to put this on first, and the second problem is that that is not the nitrogen that we want. You can, however, reduce that. You can reduce that by using HCl and zinc. That was that special recipe, that side recipe that we learned in that previous chapter. So that will reduce that to aniline in this case. Well, that looks much more like what we want. So we can see a series of steps that would put the NH2 onto the ring. So much for the NH2. How can we put the OH onto the ring? Now, we didn't have a an electrophilic aromatic substitution reaction for that. If you remember, we had sort of three weird mechanisms for putting things onto benzene rings. We had electrophilic aromatic substitution, where you turn something into such a good electrophile that even benzene will react with it. And you learn things like halogenation and sulfonation, nitration, the Friedel-Crafts reactions, but we didn't learn how to put an OH onto the ring that way. Indeed, when you think about an OH, you think about it usually as a nucleophile, not as an electrophile. And then it hits you. The second mechanism we learned was nucleophilic acyl substitution. In order to put an OH on the ring, and you would have drawn this on an exam question on that aromatic substitution exam, in order to put an OH on the ring, to do a substitution, you have to have a leaving group always for any substitution. The halogens are great leaving groups. And we also needed a strongly electron withdrawing group on the para position. And if you remember, that was NO2. And when you treated that with sodium hydroxide, you did the substitution. So you ended up getting the same product, but the hydroxide kicks the bromine off. If you remember, you get that four structure Meisenheimer complex as the intermediate. And you end up doing the substitution like that. Interesting. Interesting that this is something that appears in this other formulation. So now we know what we have to do. We just have to treat it with sodium hydroxide, but make sure that all these things are on it. Okay, so now everything is coming together. Let's think. We know that in order to do this, we have to have these two things on the ring already. We know how to put the NO2 on. We use nitric acid and sulfuric acid. That's what's happening here. How do we put the bromine on? We could put the bromine on a ring. And we've seen this even just in previous exercises in this chapter. If you use Br2 and then just the catalyst to turn it into a really good electrophile, FeBr3, or you could use AlBr3. You could even use chlorine. You could use Cl2 and AlCl3 if you wanted to. And that's just going to put a halogen onto the ring. Oops. Okay. So we sort of have all the recipes we need. We just have to figure out the order that we need to do them in. Okay, first, if we're trying to make this, you'll notice that they are para. But the NO2, the nitro group, is a strong deactivator and a meta-director. So you can't put that on first, because then the bromine would add on the meta positions. But here, it's on the para position. The bromine is an ortho-para director, so we can put that on first. We can put on the bromine, and once that's there, that's an ortho-para director. So if we do the nitration, HNO3 and H2SO4, we're going to add a nitro group. And remember, the nitro group is pretty bulky. Now, technically, we will get some ortho product, but the vast majority of our product is going to be the para product. And the reason for that is because the nitro group is big. Drawing it out here so you can see that. And also the bromine is really big. Bromine is a good leaving group and a strong nucleophile because it's such a big atom. And so steric hindrance will prevent most of the ortho product, which would look like this. It would prevent most of that from forming. You'll have a tiny bit, but okay. I drew that there, but really our focus is the story of this other carbon chain. And so we're going to work with this. Now that we have those two things on there, we can turn the bromine into an OH to the nucleophilic aromatic substitution. So we can react this with NaOH. The OH acts as a nucleophile and kicks this leaving group off. And now we're very close to having this molecule that we want. We just want to turn the NO2 into an NH2. And we saw that the recipe for that was HCl and zinc. So we can reduce that by using HCl and zinc, and that will leave us with this, this product. So it's kind of fun to weave our way through those aromatic substitution reactions. And you can see how significant now, in the last few videos, this one and the last two, you can see how significant those aromatic substitution reactions are. We talked about the significance of benzene, how it's present in so many biologically active molecules because it has such a rigid shape. So it reliably fits into receptor sites and reliably communicates messages. And so to create molecules that have that incorporated, you often have to do these nucleophilic aromatic substitutions. Those put things on the benzene ring, but rarely are biologically active molecules so small. Usually you have to make them a little bigger, and that's where the reactions in these other chapters come in. Often the nucleophilic acyl substitution. So now that we have that amine, now that we have this structure, we can just react it with our acid anhydride. And you may look at this and say, well, wait a second. I have two nucleophiles. Which one's going to attack the carbonyl carbon? And they both will try to attack. But the nitrogen is actually a better nucleophile than the oxygen is. If they're both neutral, this is if they have charges. If they're both neutral, the nitrogen is a better nucleophile than the oxygen, and that's because it's a slightly bigger atom than oxygen is. Remember, the difference between the power of a nucleophile and the difference between a base and a nucleophile largely has to do with its polarizability. Let's say these are two atoms. If there is a positive charge here, an atom that's really big has sort of a lot of front row seating for its electrons. Sort of like if you have a plasma ball that they sell in those science stores that have those like tendrils of electricity that go from the center to the glass sphere. You put your hand on it, all the electricity goes to your hand. Similarly, with these big atoms, their electrons are usually spaced out. But when you put a positive charge there, they all can line up right next to it. And you get this big, slight negative charge on one side of the atom. Which is ironic because if it were just floating around in general, it would be stable because it's so big. But because there's a positive charge right next to it, all the electrons in the whole big atom can get a front row seat really close to it. And you end up with these dipoles in one atom. The atom is polarizable. And that makes it a good nucleophile. Small atoms can't do that because they have sort of less front row seating. If the electrons try to get all on one side, they get close to each other and repel each other. And so they spread each other out more evenly over the atom. So they can't sort of compound or intensify their electric charge by putting it all on one side of the atom. So atoms get bigger as you go left and down. It's the exact opposite trend as electronegativity. Electronegativity is how much a nucleus attracts electrons, and so it attracts electrons and tends to make atoms shorter. So electronegativity and atomic size have the opposite trends. And nitrogen is further to the left on the same row 2A, or row 2, than oxygen. And so it's a bigger atom, and so it's a better nucleophile, so it's going to preferentially attack the carbonyl here. The lone pair attacks, you get nucleophilic acyl substitution, and you end up with your product. So this gets kicked off as a leaving group. Right, at the first step you get the tetrahedral intermediate, but then when it snaps down it kicks this leaving group off, and our molecule is left on there. So we'd have that little acetyl group bonded to a nitrogen. After a proton transfer, that nitrogen will only have one hydrogen. And then that nitrogen is bonded to a benzene ring that has an OH on the para position. And that is Tylenol. That is acetaminophen. Acetaminophen from the vapors of gasoline. It's kind of beautifully exciting.